For this video, I will introduce to all of you the trigonometric identities. Let's start. Now recall, for any angle in unit circle, the sine of theta can be represented as y, the cosine theta can be represented as x, and tangent theta is the slope, so we have y over x, or sine over cosine. This implies that tangent theta is sine theta over cosine theta. Now, let us give some random values or random angles for theta. For convenience, we have to use special angle. So, let's say 60 degrees. So, let theta be 60 degrees. So, we have tangent 60 degrees is equal to sine 60 degrees over cosine 60 degrees. Now, evaluating this, on the left part, we have square root of 3. Then, on the right part, sine 60 over cosine 60 will be square root of 3 over 2 all over 1/2. Now, simplifying the right part, we will obtain square root of 3. So, they are equal to each other. Now, let's say our theta for now is 30 degrees. So, simplifying, left part, square root of 3 over 3. On the right part, we have 1/2 over square root of 3 over 2. Simplifying the right part, we will obtain 1/2 times 2 over square root of 3. Cancel 2. Then we have 1 over square root of 3. Rationalizing, we have square root of 3 over 3. And they are now the same. Now, let's say our theta is 45 degrees. So we have 1 equals sine 45 is square root of 2 over 2. Cosine 45 as is. Now, they are the same number. Any number divided by itself is just equal to 1. Now, on this equation, we provided some special angles and we saw that this is true for some value of theta. Actually, this is true for all values of theta, no, in general. So this equation is called identity because it is a true statement for all values of theta, except those when cosine theta is equal to 0, of course, because if 0 is the value of cosine theta, then we will obtain an undefined statement. So now, we are on the position to define what trigonometric identity is. So it is an equation that is true for all values of the variable for which the expressions in the equations are defined. So we have plenty of trigonometric identities. Tangent theta equals sine theta over cosine theta is one of them. So let us check or let us see what are the other trigonometric identities. Now, based on our previous lesson, so these are the defined ratios of trigonometric functions, and let us focus on last three parts. We have cotangent, secant, and cosecant. Cotangent, we all know already that it is the reciprocal of tangent, so we will have cotangent theta equals 1 over tangent theta. Multiplying tangent theta both sides, we will have tangent theta times cotangent theta equals 1. Secant is the reciprocal of cosine. By performing the same procedure, we have cosine theta times secant theta equals 1. And lastly, cosecant theta is the reciprocal of 1 over sine theta. Similarly, we have sine theta times cosecant theta equals 1. And these are the first three trigonometric identities we have. Or, you may start on our first three trigonometric functions, which are sine, cosine, and tangent, and the result is the same on our previous outcome. Now, let us put on the table those generated trigonometric identities to avoid any confusions. Let's have some more identities. Tangent theta is sine theta over cosine theta. This is the identity we had on our first slide. Cotangent theta is cosine theta over sine theta. So these two will join our previous identities inside the table. Here, we need a right triangle. A right triangle whose hypotenuse is 1 unit, since this came from a unit circle. We need this in order for us to complete the trigonometric identity table. Now, by Pythagorean Theorem, we have x squared plus y squared is equal to 1. Now, x is cosine, y is sine. So we can substitute that. We have cosine squared theta plus sine squared theta equals 1. Sine squared theta is equal to 1 minus cosine squared theta. You can verify. Also, we have cosine squared theta equals 1 minus sine squared theta. So these three identities are called the Pythagorean identities. So we can now put this on our table. Note, we can acquire the last two remaining identities from cosine squared theta plus sine squared theta equals 1. Let us divide sine squared theta from both sides of this identity. Cosine squared theta over sine squared theta is equal to cotangent squared theta. Sine squared theta over sine squared theta, 1. 1 over sine squared theta is cosecant squared theta. Right? That's it. This identity. So, we have cotangent squared theta plus 1 equals cosecant squared theta. Now, solve for cotangent squared theta. We have cosecant squared theta minus 1. So, this is our second to the last identity. Another, cosine squared theta plus sine squared theta is equal to 1 from this identity. At this point, we have to divide cosine squared theta from both sides. Okay? Now, cosine squared theta over cosine squared theta is just equal to 1. Sine squared theta over cosine squared theta, that is tangent squared theta. 1 over cosine squared theta is equal to secant squared theta. Solving for tangent squared theta, we will obtain secant squared theta minus 1. And this identity will complete our table of trigonometric identities. Now let us have an example. Prove that 1 minus sine beta times the quantity of 1 plus sine beta plus sine squared beta is equal to 1. Solution number 1. So this is given. From this identity, we're going to show that the left part is just equal to 1. How we're going to do that? These terms, 1 minus sine beta and 1 plus sine beta, we're going to apply FOIL method. So that will be 1 minus sine squared beta. You can verify. Then as is sine squared beta. By doing associative property, so we can simply perform negative sine squared beta plus sine squared beta first. So that is just equal to 0. So that will cancel. So the remaining part on the left side is 1. Then they are now the same. Solution number 2. This is given. Now, by performing what we did on solution number 1, we have 1 minus sine squared beta plus sine squared beta. Here, in trigonometric identities, 1 minus sine squared theta is cosine squared theta. But here, in this example, we just use beta. So, 1 minus sine squared beta is just equal to cosine squared beta. As is sine squared beta. Now, this identity, cosine squared beta plus sine squared beta, is equal to 1. Now, 1 is equal to 1. So that will end our proof for this example. Now, another example, show that the secant squared phi times tangent squared phi minus tangent squared phi is just equal to tangent to the fourth of phi. Solution number 1. So this is given. Now, let us show that the left part is just equal to the right part. Observe that tangent squared phi is given on both terms. So we can factor out that tangent squared phi. So that will be tangent squared phi times the quantity of secant squared phi minus 1. Here, secant squared phi is this identity, tangent squared phi. So we can substitute that. We have tangent squared phi, and now bring down tangent squared phi on this part. So this quantity is tangent squared phi based on this identity. Now, by multiplying these terms, tangent squared phi times tangent squared phi is equal to tangent to the fourth of phi. And they are now the same. And for solution number 2, I dare you to show your own proof that this identity is true for all values of phi. Another example, prove that the tangent z times sine z plus cosine z is equal to sec z. Pangit pakinggan, no? Gawin na natin secant z, no? So, first solution, this is given. Let us show that the left part is just equal to secant z. Yeah. Tangent z is just equal to sine over cosine. So, we have sine z over cosine z. Then, bring down sine z and cosine z. Okay. Next, evaluate this part. So, sine z times sine z, that will be sine squared z over cosine z. Bring down cosine z on our second term. Then, evaluate this. This fraction, so we all know that we have a denominator of 1 on this part. So, by doing butterfly method, we will obtain sine squared z plus cosine squared z over cosine z. You can verify that. But sine squared z plus cosine squared z is equal to 1. Right? That's equal to 1. So, we can use that identity to obtain 1 over cosine z on the left part. But 1 over cosine z is equal to secant. So, secant z. And now, our job is done. For our last example, prove that secant x over sine x minus sine x over cosine x is equal to cotangent x. Okay. So, this is given. Secant x is equal to 1 over cosine x, right? So, that's our second identity on our table. Okay. So, we can change that from secant x to 1 over cosine x. Then, as is, yung ating mga terms na natira. Okay. Evaluate this one. So, 1 over cosine x times 1 over sine x. Simplifying, we have 1 over cosine x times sine x. Okay. Then, of course, bring down sine x over cosine x. Now, by doing butterfly method on this part, we will obtain cosine x minus sine squared x times cosine x all over cosine squared x times sine x. Notice, on our numerator, cosine x are present on each term. We can factor out that cosine x. So, we will have cosine x times the quantity of 1 minus sine squared x all over cosine squared x times sine x. Here we can cancel cosine x. Since the cosine of the denominator has an exponent of 2, we have a remaining single cosine. So on this part, single cosine x, right? So we will obtain 1 minus sine squared x all over cosine x times sine x. Now for continuation, 1 minus sine squared x is equal to cosine squared x. So that is just cosine squared x. Then denominator as is cosine squared x all over cosine x. So cancel, we have a remaining of single cosine x on numerator. And now that will give us cosine x over sine x. But the expression on the left part is equal to cotangent x. Hence, we can say that cotangent x on the right part is just equal to cotangent x on the left part. And now, we just prove our given identity. And that is it, guys. Thank you so much for listening. I hope that you learned a lot on this video. See you guys and God bless.